Welcome back, everyone. In this video, we will begin discussing antiderivatives. Now, an antiderivative, what exactly is an antiderivative? Well, it probably sounds exactly like how I'm going to describe it. It is the opposite of a derivative. Now, when you formalize it, it does seem kind of weird at first. So it says an antiderivative of a function f, so lowercase f, is a function capital F, such that when you do the derivative of the capital F, you get back the lowercase f function. So in words, it is a function that when you take the derivative of it, it gives you back the original. Now, for example, an antiderivative of the function 2x is x squared. And the reason that is the case is because the derivative of x squared, the one thing we're calling the antiderivative, or a antiderivative, I should say, x squared, when you do the derivative of x squared, you get 2x. So you get back to the original. Well, one thing that's going to happen, and we have to jump into this right away when we talk about antiderivatives, is that when you do the derivative, so when we do the derivative of x squared, we could have had numbers added onto it because the derivative of a number is 0, and it's not going to change the fact that we would get back to 2x. All right, so for example, for f of x equals 2x, the following are all antiderivatives of f of x. All right, so everything I write below, all the functions below I write are going to be antiderivatives. Now I should specify that this notation using a capital F to represent the lower case f's antiderivative, that's just a general thing. It's not like the derivative notation like a prime. So we still have to write that f prime, capital F prime equals lowercase f. Right, so you could use g or any other letter to say the antiderivative function. This is just the normal way to write it. All right, but all of the following are antiderivatives. So the one that we described above is x squared. And then I'll just write here, since I didn't actually do it out, I just kind of wrote it. It's because the derivative of this capital F, x squared, is 2x, and it matches the original f of x. So it's an antiderivative. Well, what happens if I just do x squared plus 1? Well, that's still an antiderivative, because if I do the derivative of x squared plus 1, I get 2x plus the derivative of 1, which is 0. So it's still 2x. And I can do plus or minus any number. So I can do f of x equals x squared minus 7, just throwing out a random number here. And then the derivative of this is once again 2x. Well, what happens in general is that whenever you do an antiderivative, you can always get your sort of base formula, like the x squared here is sort of like our base formula. We don't have anything added onto it. And you add on a plus c. So in general, what we will say is that the antiderivative, I'm using the word general because they will call this the general antiderivative. The antiderivative of f of x equals 2x is capital F of x equals x squared plus this capital C. And C is just a number. It's called the constant of the antiderivative, but it's just a number. Right, and C is the typical letter to use. If it's already used in your formula somewhere, maybe you have some sort of word problem that already uses the letter C, you can use any letter at all. We typically just use capital C because it's not really used for much. So it's usually pretty safe to use, and it stands for constant. So that's why. But typically when you do antiderivatives, if C is taken, you'll just do you'll use other capital letters that are close to C, like A or B or D. You could even use E as long as it's uppercase, because a lowercase e means that 2.71 number, but we could do something like that. All right, now in some problems, we will be able to solve for C, and other problems we will not. And it just depends on what you're given. But one thing that's important to figure out here, just write down, is when a c value is specified, even c equals 0, like f of x equals x squared, that's when c equals 0. We call this a specific antiderivative. And when c is not specified, we call this a general antiderivative. So just in terms of what we have above, all of these are specific antiderivatives because we all have c. C is 0 here, c is 1 here, c is -7 here. These are specific antiderivatives. And then the f of x plus c, that is the general antiderivative. Now, what we'll see very quickly when we start working problems is that you always find the general antiderivative first. Then if you're given extra information, you'll be able to solve for c. And we'll see what that looks like when we go through problems as well. But typically in problems, if you are not able to solve for c, you're going to have to be told what letter to use for your antiderivative constant, like a c here. You might be told to use other letters, but if you're not told to use specific letters, then that means you're going to be able to actually solve for c or whatever letter you use. Right, so before we jump into it, we actually know a lot of antiderivatives already because we know how to do the derivatives of a lot of things already. Now, it's not going to be everything because just like with derivatives, you have other general rules. So things you won't see in here, and I'll go through and describe these, but things you won't see in here, you won't see anything that would be sort of like the chain rule, meaning we knew how to do the derivative of x squared very quickly. That was the power rule. But then when we had like cosine of x squared or something else with x squared in it, we had to be able to use the chain rule. So you're not going to see anything yet related to a chain rule. Really, this is going to be just all the quote unquote basic formulas. Now, in the upper left-hand corner, I have the general properties. There's two of them, but they're the same general properties of derivatives. And it's probably been so long since we specified them that maybe you haven't thought about them for a while. But these two properties say that if you want to do the antiderivative of a number times a function, you just leave the number alone. So we leave constants alone as long as they're multiplying a function. So if they're just a constant by itself, like if we had to do the antiderivative of x squared plus 1, we would have to deal with that differently. But if it was 2 times x squared, we just leave that 2 alone. So we leave constants alone as long as they are multiplying functions. And then the second one here, so that is actually the same general property of derivatives. I originally talked about it factoring out numbers outside the derivative, and then we just realized it's the same as leaving it alone. So the other one is if you're adding or subtracting functions, you just do the derivative or antiderivative, in this case, of each part. So we do the antiderivative of each part if you have addition or subtraction. So just like with derivatives, we don't start off with multiplication or division. If you see multiplication or division at this point, that means you're going to have to algebraically simplify it before you use and compute the antiderivatives. I'll go ahead and warn you that eventually there will be a product rule for antiderivatives. I'm not going to talk about it now because it's quite a ways in the future. So there is that. There is really no ever going to be a quotient rule for antiderivatives. So pretty much anytime you see a fraction when you're integrating, actually I'm kind of spoiling a word here. We don't talk about integrals yet, but anytime you do an antiderivative of something with a fraction, it's going to have a formula in the original fraction, or you're going to have to simplify it somehow. All right, but the main thing here is that these are the same general properties of derivatives. So we're not going to go through the brutal detail when we started derivatives. We're just going to follow the same kind of outlines. Right. And as far as the formulas go, I have it really separated into two parts. I have these formulas that don't involve just trig functions, and then I have the trig antiderivatives. And the reason I have them separated is very often with the trig antiderivatives, the formulas look kind of weird. So I wanted to just have them completely separate and be able to focus your eyes on them alone. All right, so the trig antiderivatives. What is going on here in all these formulas is that you have the function on the left side and then its antiderivative on the right side. Now, this is pretty much the same way we write any table, the table of derivatives, the properties of limits. We have whatever we're starting with and whatever we want to finish with. So this says the antiderivative of cosine of x is sine of x. Right, if you want to understand why that is true, that's because when we do the antiderivative's derivative, so if we do the derivative of sine of x, we get back cosine of x. Now the function formula, you'll notice here, this is always going to be the kind of simplified one, meaning there's not going to be negative signs unless if there's just a negative sign in our formula somewhere. All right, so these are kind of the main two, the antiderivatives of sine and cosine, that draw the most confusion because they do the opposite of your derivative formula. So the derivative of cosine is negative sine, but the antiderivative of cosine is positive sine. Well, the antiderivative of sine is negative cosine. And the reason for that is if you do the derivative of negative cosine, you get back regular sine. Because the derivative of cosine is negative sine, and then you get a double negative. So just remember, it's kind of the opposite when it comes to sine and cosine when you're doing the antiderivative. Now the other four rules I think always look kind of funny because the function formula, like doing the antiderivative secant squared of x is tangent of x. It just really has to be like that because the derivative of tangent of x is secant squared of x. So one thing you won't see, at least yet, because it's far in the future developing techniques, we're going to be able to do the derivative of secant squared of x. We cannot do the derivative of any other power of secant at this point, not even secant cubed, not just secant without any power, so secant to the first power. It has to be secant squared. For a similar reason, since the derivative of secant of x is secant of x times tangent of x, when you do an antiderivative with secant of x times tangent of x, its formula is secant of x, but it can't really be written any other way. You can't have secant squared of x times tangent of x, right? Because it would be like a combination of these two rules, and we can't do that. We have to use these rules very literally. So as you go through these sections with antiderivatives, until we start to develop more formulas, you're not going to see really anything else. And another thing I wanted to point out again, like I described at the beginning, is that things related to the chain rule aren't popping up yet. So you'll notice there's an x inside every one of these. There's not a 2x, there's not an x squared. There can't be a, like a u replacing some function for the chain rule if you thought about it like that before. But I wanted to take a moment just to really talk about the trig rules specifically because the formulas, the starting part of the formulas, the things we're going to look for when we try to do antiderivatives are most of the time more complicated than we would expect. When we do derivatives, if we saw cosecant squared in the derivative, we would think, okay, we got to do the chain rule. The derivative of cosecant is this, and start with the power rule and do all this stuff. Well, when you do the antiderivative of cosecant squared of x, it's just negative cotangent of x. That is the rule, and it's because the derivative of cotangent of x is negative cosecant squared of x. All right, now as far as these other formulas go, most of them, I think reading them are relatively straightforward, but once again, you have this notion that the formulas that we start with can be a lot messier than the formulas we end with, which is really the opposite of derivatives. But I wanted to go through these, especially the first few, and really talk about them. So the first one, it says the function k, and k is just a number. Its antiderivative is a number times x. Right. So this is sort of a special one, sort of like when we did the derivative of just a number way back when we introduced derivatives of numbers. The derivative of just a number was 0. The derivative of a number times x was just that number. Well, this is the opposite one for that second example. The derivative of a number times x is a number. So what this first one says is that the antiderivative of a number is a number times x. And that one's so important that it's probably just good to keep it separated. Antiderivative of a number equals number times x, or whatever your letter is. Now the next one is sort of like our power rule for antiderivatives, because the function formula is x to the n. Now the way the power rule works for antiderivatives is really the opposite. So the power rule for derivatives, you bring the power down and then you subtract 1. Well, when you do that in reverse, what you do first is you add 1 to the power, and then you divide by the new power. So that is the power rule for antiderivatives, and just like with derivatives, it's really good to remember the wording. Knowing the formula, of course, helps, but knowing the wording is almost more helpful for a lot of these. Now, there is a condition here that n cannot be -1. Why? Because when n is -1, not only can you not use this formula because you'd have division by 0, but the antiderivative of 1 over x is already a special formula, and it is the natural log of the absolute value of x. So x to the -1 would be exactly this with n equal -1. We can rewrite that as 1 over x. Now you should be prepared to see both of these, and of course you should be very comfortable with rewriting x to the -1 as 1 over x, or if you would like 1 over x to be rewritten as x to the -1, it's fine. But its derivative or antiderivative is the natural log of the absolute value of x. And one thing that's really important is these absolute value bars. Right, so we know that the derivative of the natural log of x is 1 over x, but why are these absolute values there? Why are they important? Well, the reason they're important is when we did the derivative of 1 over x way back when, we talked about the graph here. So the y equals 1 over x, and then our base graph was the natural log of x. So the derivative of the natural log of x was 1 over x. And we talked about this idea of the domain, and that when you do the derivative of something, your domain can't get bigger. So the natural log of x had domain from 0 to infinity. Well, 1 over x has domain including negative x values, but when we talk about the derivative, we're not really including this. The problem is when we start with 1 over x. So when we start with the red graph, our domain is everything except 0. We can't plug in 0, but we can plug in a negative number. Well, the natural log of x isn't good enough anymore because we need to be able to plug in negative numbers. Basically, the domains need to match. So when you do absolute value of x, and in Desmos, that's just ABS. When you do the absolute value of x like that, then it allows you to actually compute the antiderivative everywhere. It includes the negative numbers and positive numbers, and only 0 is left out. Right, so that absolute value is important. If you forget it, you're wrong. You know, it's very close to being right, of course, but you're wrong. So you need to make sure you include that absolute value. The only times you don't need it is if you're told that x is positive, because if it's positive, then we don't need to include this side, so we can get rid of the absolute value. So just keep that in mind. Unless if you're told x is positive, you need to absolutely make sure that you use the absolute value on the x. Right. Now, probably the easiest one is the antiderivative of e to the x because it is itself. The reason for that is the derivative of e to the x is itself. Now, we really didn't do any examples with these, but they're more common when you talk about antiderivatives, so I wanted to bring these in as well. When you do the antiderivative of b to the x, so something like 2 to the x, then you get back itself, 2 to the x, and then you divide by the natural log of 2. All right, so I'll just kind of write a very quick example on over here because we won't see it often, but just to point it out, what it's saying here, the antiderivative of 2 to the x, this is the specific one because of course in general we have a plus c, is 2 to the x over the natural log of 2. Now, you may not remember the derivative of 2 to the x, but it is 2 to the x times the natural log of 2. So we do the opposite. Since there's a times, when you do the antiderivative, you have a division. And the last three I have here are the inverse trig functions. Now keep in mind that you have the hyperbolic functions as well, so you can look at any formula that we had for derivatives, but these are the main ones. All right, now for inverse trig functions, the derivative of arc sine was 1 over the square root of 1 minus x squared. So the antiderivative of 1 over 1 square root of 1 minus x squared is arc sine or sine inverse. So the next one comes straight up from cosine because this is the derivative of arc cosine of x. Now, very often you won't actually see a formula for arc cosine of x as far as the antiderivative goes. And the reason is because of this property here. What's the difference between this one and this one is just this negative sign, which is really a -1. So if I got rid of that, this would be arc sine. Well, what this is really saying is if I throw the negative on here, then I could say this is negative arc sine, but I could also say it's arc cosine. It's totally up to you whether you want, if you see this negative here, you think of arc cosine, or you more so think of negative arc sine. You can use either one. And then arctan was different. It was the derivative of arctan was 1 over 1 plus x squared. So there's not a substitute for that one. You have to know that one as well. So what I want to go ahead and do real quickly, and then we'll get started on the problems, is the next video is just talk about real quickly the antiderivatives of the three hyperbolic trig functions. I wanted to save these last because one thing you might remember about the hyperbolic trig functions is their formulas look almost the same. So what's the antiderivative of hyperbolic sine, hyperbolic cosine, and hyperbolic tangent? Now, one thing you might remember is that with sine and cosine hyperbolic functions, they were all positives. So the derivative of hyperbolic sine of x was hyperbolic cosine of x, positive, and the derivative of hyperbolic cosine of x was positive hyperbolic sine of x. So these are both positive. Now the question is, do you remember what the derivative of hyperbolic tangent of x was? And if you do, one thing I just realized I did is this should be in the other column because we're doing antiderivatives. So it's the simpler looking formulas in the antiderivative column. The derivative of hyperbolic tangent, well, it's pretty much the same thing as the regular one as well. And it was also positive. Oop, but I can't forget the h for the hyperbolic part. So it's hyperbolic secant squared of x. And like I mentioned back then when we talked about these hyperbolic trig functions, is that yes, you can worry about the other three, but they are so rarely used. Hyperbolic functions are so rarely used in the first place, but using hyperbolic trig functions that aren't hyperbolic sine, cosine, or tangent are so rare that we're not going to worry about them just like we didn't back then. Right. Now, these formulas, just like with the others, you want to make sure, you think about it. If I see a hyperbolic secant squared of x, I know the antiderivative is hyperbolic tangent of x. If I only have a single power of hyperbolic secant, then I cannot do that yet. So there's probably an error some way. Now, just a quick important note before we actually start computing antiderivatives, and that's pretty much what I said at the beginning. But you do not, if you don't have a rule for computing an antiderivative, don't make one. Right? You do not have a way to compute antiderivatives with multiplications or divisions. You do not have a way to compute antiderivatives somewhat with this chain rule. So everywhere you see an x in all of these formulas, if you had a 2x, you just can't do it yet. And it's not as obvious how to do it, make up for the chain rule with antiderivatives. So it's quite a few sections before I start talking about that. But do remember that you're not going to be asked a question that you cannot do using one of these rules. So if you do have a multiplication, maybe FOIL it out. If you have a division, break it up and make a whole bunch of fractions and simplify each fraction, and it should be just fine like that. But I'll see you in the next video when we actually go through the problems.